You know, it's funny how we use words every day without really stopping to think about their precise meaning. Take work.
Hmm.
You might say you've done a lot of work after a day, like filled with mental gymnastics or maybe running around. But what if I told you that, according to physics, you might not have done any work at all?
Right, like pushing a wall.
Exactly.
Hmm.
Imagine pushing against a brick wall with all your might. You're sweating, muscles burning. Physics might just shrug and say, nope, no work done here.
Yeah, it's a very specific definition.
Okay, let's unpack this fascinating difference between our everyday feel for it and the scientific definition. We're going to take a deep dive into work, energy, and power.
And what's fascinating right off the bat is just that precision in physics, our gut feeling of effort. It doesn't always line up with scientific work.
Not at all.
So yeah, over the next little while, we're going to be dissecting these ideas, work, energy, power, using a really solid chapter as our guide.
Yeah, it looks pretty comprehensive.
It is. Think of it as getting straight to the insightful core. We'll look at the formulas, the units, the different types of energy, and the big one, the principle of conservation.
Yeah.
Our aim isn't really to drown you in detail, but more to pull out those aha moments, the things that clarify how the physical world really operates.
Exactly. So let's tackle work first. Our source material is really clear. In physics, work isn't about effort, not really.
Yeah.
It's specifically about a force causing an object to move.
Mm-hmm. Displacement.
There has to be displacement. Think about a cyclist. Their legs are definitely exerting force, right? And the bike moves. So work is being done.
Right. Or a horse pulling a cart. Same idea.
Same idea. But that person pushing the wall, force, yes, tons of it maybe.
Yeah.
But no movement, no displacement.
So no work.
Therefore, no work by that specific force. That's the key, isn't it?
It's a crucial distinction, yeah. And the example of the coolie standing perfectly still with a heavy load, that really drives it home.
Right.
I mean, they're undoubtedly exerting an upward force, fighting gravity, and biologically, physiologically, they're working hard. No question.
Sure feels like work.
But because the load isn't moving vertically, the displacement in the direction of that lifting force is zero. Hence,
Yeah.
the work done by that lifting force on the load is zero. It's all about the effect of the force on the object's motion, specifically in the direction of the force.
Right. It's not just applying a force. It's that force-achieving movement along its line of action. No, it's not just yes or no, work or no work. The chapter explains the amount of work depends on things, too.
Right, it depends on how much a force.
And how far the object moves in the direction of that force. Push harder, move it further. You've done more work.
Which thankfully kind of matches our intuition.
Yeah, that part makes sense.
It does. And to put a number on this, we get the formula. WEF times S times cosine theta.
Okay, let's break that down. W is work.
F is the magnitude, the strength of the force. S is the magnitude of the displacement, how far it moved.
And the cosine theta. That sounds important.
It's really important. It basically handles the angle, theta, between the direction the force is pushing or pulling and the direction the object actually moves.
So they might not be perfectly aligned.
Exactly. And only the component of the force that's along the direction of motion actually contributes to the work done.
Okay. Let's dig into that angle then. First case. What if the force and the movement are in the exact same direction?
Right.
So theta is 0 degrees.
Right. Cosine of 0 is 1. So the formula just simplifies to W equals F times S.
Perfect. Straightforward.
Makes perfect sense. If you're pushing a box and it slides straight forward, you're doing positive work. The chapter gives a freely falling body as an example. Gravity pulls down, it moves down.
Positive work by gravity.
Positive work done by gravity. Same with a coolie, lifting a load. Upward force, upward movement, positive work done by the coolie.
Got it. Okay, next case. What if the force and the displacement are at right angles, perpendicular? Theta equals 90 degrees.
Well, cosine of 90 degrees is 0.
So the work is 0.
The work done is 0. W equals 0, 0. And this one can feel really counterintuitive.
Yeah, it sounds weird.
Think back to that coolie walking with the load, but on level ground now. They're still exerting that upward force to hold the load.
Yeah, against gravity.
But they're moving horizontally. The lifting force is vertical. The motion is horizontal. They're perpendicular.
So the lifting force does no work in moving the load sideways.
Exactly. In terms of the horizontal motion, that specific lifting force does 0 work. Even though, again, they're clearly expending energy just to hold it up.
Wow, okay.
Yeah.
That's different.
It is another classic example.
Wow.
Something moving in a perfect circle at constant speed. like a ball on a string you're whirling around.
Okay.
The tension in the string, the centripetal force, constantly pulls the ball towards the center.
Right, otherwise it flies off.
But the ball's motion at any instant is along the tangent to the circle. It's always perpendicular to that inward pull.
90 degrees again.
Always 90 degrees between the force and the instantaneous velocity. So that centripetal force does no work on the ball. It changes the direction, keeps it in the circle, but doesn't speed it up or slow it down.
That's a mind bender. A force causing motion but doing no work. Okay.
Yeah.
So what about the last main case? Force and displacement are in exactly opposite directions. Theta equals 180 degrees.
Okay, so cosine of 180 degrees is -1.
-1, so the work is negative. WNEFFS.
Exactly. Negative work.
Hmm.
This means the force is acting against the motion. It's essentially trying to stop it, or it's taking kinetic energy away from the object.
Like friction.
Friction is the perfect example. You slide a book across a table, it slows down and stops. Friction acted opposite to the motion, did negative work.
Okay.
Or think about throwing a ball straight up. As it rises, gravity is pulling down. The displacement is up. The force of gravity is down. Opposite direction.
So gravity does negative work on the way up.
Negative work, yeah, which is why it slows down, stops, and then comes back down.
So negative work is like the force is, I don't know, undoing the motion or working against it. Our source also mentions forces that aren't constant. That sounds more complicated.
It is a bit more complicated, yeah. If the force changes as the object moves, you can't just use F times S. You have to kind of break the movement down into tiny little steps where the force is almost constant.
Okay.
And you calculate the tiny bit of work done in each step, and then you add them all up. Graphically, if you plot the force versus the displacement, the work done is actually the area under that curve.
Calculus sneaks in.
Just a little bit, conceptually.
Okay. Now, what about the work done by gravity specifically? The chapter gives the formula W equals as mgh, mass times gravity times the vertical height change.
Right.
But what's really interesting is it says the path doesn't matter. Straight down some stairs, down a ramp.
Yeah.
The work done by gravity only depends on that vertical drop h.
That's a key property of gravity. It's what we call a conservative force.
Mm.
For forces like gravity, the work done moving an object between 2 points doesn't depend on the path you take.
Okay, that's useful.
It is. But the direction still matters for the sign, like we discussed. If an object moves up by height, gravity is pulling down, so the work done by gravity is negative mv bar.
Right, opposite directions.
If it moves down by height, gravity pulls down, motion is down, so the work done by gravity is positive μ.
Same direction.
And if you lift something up against gravity you're pushing up, it moves up, so you do positive mech work. You're basically storing that energy.
Storing it.
Yeah.
Okay, we'll get back to that with energy. Got it. Up means negative work by gravity. Down means positive work by gravity. Now, units. You mentioned the formula gives work. What's the standard unit?
The standard SI unit for work is the joule, symbol J.
And what is 1 joule exactly?
1 joule is defined as the work done when a force of 1 Newton moves an object through a distance of 1 meter in the direction of the force. So 1J equals 1 NME.
Okay. And obviously, we can have bigger amounts.
Yeah, you often see kilojoules, kJ, megajoules, mJ, even gigajoules, GJ, for really large amounts of work or energy.
The chapter also mentions an older unit, the erg.
Ah, yes, the CGS system unit, the erg. It's much, much smaller than a joule. 1 erg is the work done by a force of 1 dyne moving an object 1 centimeter.
Tiny.
Very tiny. The conversion is 1 joule equals 10 million ergs. So 1J equals 107 erg. Joules are definitely more practical for everyday physics.
All right, I think we've wrestled with work pretty well. Let's switch gears then. What about power?
Power. Okay, so if work is about getting something done by applying force over a distance, power is all about how fast you do it.
The rate.
It's the rate of doing work. The formula is P equals a day. Power equals work divided by the time taken.
So doing the same work faster means more power.
Exactly. Our chapter had that nice example of 2 coolies lifting the same load to the same height. They do the same amount of work against gravity.
Right.
But if one coolie does it in, say, 10 seconds and the other takes 20 seconds.
The first one is more powerful.
Twice as powerful, in fact. Same work, half the time, double the power output.
Okay, that makes sense. Is there another way to think about power?
Yeah, there's a useful relation if the force is constant and acting in the direction of motion. Power can also be calculated as PAF times V force times velocity.
Oh, interesting. How does that work?
Well, work is force times distance. W is Fs. And power is work divided by time. P equals WT. So power is FST. But distance divided by time is just average velocity V. So P equals FV.
Clever. So for a car moving at a steady speed, the power its engine needs to produce to overcome drag is the drag force times the car's speed.
Exactly. Useful shortcut sometimes.
Okay. Units for power. If work is in joules and time in seconds.
Then power is in joules per second, and that unit has a special name, the watt, symbol W.
Oh, the watt. We see that everywhere. Light bulbs, appliances.
Named after James Watt. So 1 watt is equal to 1 joule per second. 1 W equals 1 JS. And again, we use prefixes. Kilowatts, kilowatts, KW, megawatts, MW, gigawatts, GW for large power, and milliwatts, MW, or microwatts, AOV, for tiny amounts.
Is there a CGS unit too?
Yep, following the pattern, it's ergs per second. Ergs in the conversion is 1 watt equals 10 million ergs per second. 1 W equals 107 ergs.
And what about horsepower? You hear that for engines.
Right. Horsepower HP is an older unit, still commonly used especially for cars and motors. It's defined historically, but the standard conversion is 1 horsepower is equal to 746 watts.
746 watts. So roughly 3/4 of the kilowatt.
About that, yeah. 1 HP, 0.746 kilowatts.
Okay, so let's quickly summarize the difference again. Work is about the total energy transferred or changed by a force moving something. Measured in joules. It doesn't inherently care about time.
Right.
Power is about time. It's how quickly that work is done or how fast energy is transferred, measured in watts, which are joules per second.
Spot on. Time is the key differentiator.
All right. Work, power, that leads us naturally to energy. What's the connection there?
Energy is, in many ways, the most fundamental concept of the three. Our source defines it simply as the capacity to do work.
The capacity, like the potential.
Exactly. If a system has energy, it has the ability, the potential, to exert a force over a distance, which is the definition of doing work. Energy is like stored work, in a sense.
Okay. And the units, if it's a capacity to do work.
Then the units are the same as work. The SI unit for energy is a joule. The CGS unit is the erg.
Makes sense. But the chapter lists some other units that are really common, especially watt-hour, WH, and kilowatt-hour, kilowatt-hour. Now, those have watt in them, which we just said is power. How are they energy?
Yeah, that's a super common point of confusion, but it's crucial. Watts and kilowatts are power, energy per time. But if you multiply power by time.
Power times time, joules per second times seconds. You get joules. Energy.
Bingo. So a watt-hour, WH, is the amount of energy transferred or used if you run a device with a power of 1 watt for a duration of 1 hour.
How many joules is that?
Well, 1 watt is 1 joule second, and 1 hour is 3,600 seconds. So 1 WH is 1 JS, 3,600 S equals 3,600 joules.
Okay. And the kilowatt-hour, that's the one on my electricity bill.
Right. Same logic. 1 kilowatt is 1,000 watts. So 1 kilowatt is 1,000 watts. So 1 kilowatt is the 300 ratio 100, 3.600 J, or 3.6 megajoules. Precisely. So it's really important. Kilowatt hour is a unit of energy, not power. It measures a total amount of energy consumed or delivered over a period.
Got it. That clears up a big one. The chapter also mentions the calorie, often related to food.
Yes, the calorie cal is another energy unit originally defined in terms of heat. 1 calorie is the energy needed to raise the temperature of 1 gram of water by 1 degree Celsius.
And how does it relate to joules?
The standard conversion is 1 calorie is approximately 4.18 joules. Food energy is often listed in kilocalories, sometimes written as calories with capital C.
Okay. And one more unit mentioned for the very small scale, electron volt.
Ah, the electron volt, EV. Yeah, when you're dealing with atoms, molecules, subatomic particles, the energy involved is incredibly tiny in terms of joules. So the electron volt is much more convenient. It's defined as the amount of kinetic energy gained by a single electron when it accelerates through an electric potential difference of 1 volt.
And in joules.
It's tiny. 1 EV is about 1.6 times 10 to the minus 19 joules, 1.6 by 10 UJ, essential unit in atomic and particle physics.
Wow, okay, so energy, capacity for work, measured in joules, but also kilowatt for electricity, calories for heat food, EV for atomic stuff. Now let's get into the different kinds of energy. The chapter starts with mechanical energy.
Right. Mechanical energy is probably the most intuitive kind. It's the energy an object possesses due to its motion or its position or maybe its configuration.
And it's made up of 2 main types.
Yes, it's the sum of potential energy, U, and kinetic energy, K. So a mechanical, U plus K. And if we ignore friction and air resistance, this total mechanical energy often stays constant.
Okay, let's look at potential energy first. Potential suggests it's stored, ready to be used.
Exactly. It's energy stored by virtue of an object's position or its internal configuration. The chapter gives examples like a body raised high above the ground.
It has the potential to fall and do work.
Right. Or a compressed or stretched spring or a drawn bow. They store energy because of their deformed state.
Makes sense. And the main type of potential energy discussed is gravitational potential energy.
Yes, U equals mRAH. That energy stored in an object of mass due to its height above some reference level, where g is the acceleration due to gravity.
We saw MEC related to the work done against gravity earlier.
Precisely. The work you do lifting something against gravity gets stored as gravitational potential energy. The higher you lift it, the more potential energy it has relative to the starting point. And choosing that zero reference level is arbitrary. Only changes in potential energy usually matter.
Okay, and the chapter also mentions elastic potential energy.
Briefly, yeah. That's the energy stored when you deform an elastic object, like stretching a rubber band or compressing a spring. The more you deform it, the more energy is stored, ready to be released when it snaps back.
Got it. So potential energy is stored energy due to position or shape. What about kinetic energy?
Kinetic energy, K, is the energy of motion. If an object is moving, it has kinetic energy. Simple as that.
And the formula for straight line motion?
The standard formula is KRL1 half mv squared. KRL is the mass, V is the speed.
So it depends on mass, but it depends more strongly on speed because speed is squared.
Exactly. Double the mass, you double the kinetic energy, but double the speed and you quadruple the kinetic energy. Speed is a huge factor.
Wow. Okay. How is kinetic energy related to work?
Well, kinetic energy can be thought of as the amount of work a moving object can do because it's moving before it comes to rest. And there's a direct link through the work energy theorem.
Ah, you mentioned that.
Yes, the net work done on an object, the total work done by all forces acting on it, is equal to the change in its kinetic energy. Net equals K final initial.
So if you do positive network, you increase its kinetic energy, make it faster. Negative network slows it down.
Precisely. It's a really powerful relationship connecting forces, work, and changes in motion.
The chapter also mentions a link between kinetic energy and momentum. Momentum is PMV.
Right. You can actually rewrite the kinetic energy formula using momentum. Since P arrow mv, then V arrow pm. Substitute that into K arrow of 4.
KAPE is funny half or PF 10 over S.
Exactly. K is pt 20 meter.
This shows an interesting relationship. For instance, if two objects have the same momentum, the lighter one, smaller m, will have more kinetic energy.
Interesting. Now, kinetic energy isn't just about moving in a straight line, is it? The source mentions different forms.
Correct. We often to break it down based on the type of motion.
Yeah.
There's translational kinetic energy, which is the ham-VO part from moving from one place to another.
Straight line motion.
Or any movement of the center of mass. Then there's rotational kinetic energy, the energy an object has because it's spinning or rotating. Think of a spinning flywheel or the Earth rotating.
Okay.
And there's vibrational kinetic energy from parts of an object oscillating back and forth relative to each other, like the atoms in a solid vibrate.
And an object can have multiple types at once.
Oh, absolutely. Think of a bowling ball rolling down the lane. It's moving forward, so it has translational kinetic energy. It's also spinning, so it has rotational kinetic energy. Its total kinetic energy is the sum of both. Right. Okay, so that covers mechanical, energy potential, and kinetic.
Oh, okay.
There are loads of other energy forms, aren't there?
A whole spectrum. The chapter lists quite a few, though mostly just mentioning them. There's chemical energy.
Stored in bonds, like in fuel, food, batteries.
Exactly. Heat energy, or thermal energy, which is related to the random motion and vibrations of atoms and molecules. Light energy, carried by electromagnetic waves.
From the sun, light bulbs.
Electrical energy, associated with the flow of electric charge. Nuclear energy, stored in the nucleus of atoms, released in fission or fusion.
Sound energy, from vibrations traveling through a medium.
And then energy resources we tap into. Solar energy from the sun, hydro energy from moving water, geothermal energy from the Earth's internal heat, wind energy, even magnetic energy.
It's amazing. And the key point is that these aren't totally separate boxes, right?
Oh.
Energy changes form all the time.
Constantly. That's one of the most fundamental observations in physics. Think about almost anything happening. A power plant burns coal, chemical energy, to create heat, which boils water, thermal energy, to make steam, which turns a turbine, mechanical energy, which drives a generator to produce electrical energy.
Which then powers my lamp, producing light and heat energy.
It's a continuous chain of transformations. Eating food, chemical, allows us to move, mechanical, and stay warm, thermal. It's everywhere.
Which leads us perfectly to the really big idea. The principle of conservation of energy.
Yes, a cornerstone of physics, simply stated. Energy cannot be created or destroyed.
Cannot be created or destroyed.
It can only be transformed from one form into another, or transferred from one system to another. The total amount of energy in an isolated system, or indeed the universe as a whole, remains absolutely constant.
Wow. That's a huge statement. How do we sort of verify that? The chapter uses a falling object example.
Yeah, it's a classic theoretical verification, usually ignoring air resistance to keep it simple. Imagine dropping a ball from some height.
Okay, at the top, just before you
It's stationary, so its kinetic energy is zero, but it's high up, so it has maximum gravitational potential energy.
Right,
Total mechanical energy, 0 plus millimole equals milli h.
right. They'll let it fall.
As it falls, its height h decreases, so its potential energy goes down, but it's picking up speed v, so its kinetic energy goes up.
The potential energy is turning into kinetic energy.
Exactly. At any point during the fall, the sum of its potential energy, based on its current height, and its kinetic energy, based on its current speed, will still equal the initial total energy, weight.
And just before it hits the ground, say height is almost 0.
Then its potential energy is almost 0, but its speed is at its maximum. Almost all the initial potential energy has been converted into kinetic energy. So K up d mg and U up is 0. The total is still mg.
So the total mechanical energy, K plus U, stays constant throughout the fall.
Assuming no air resistance, yes. The energy just changes form from potential to kinetic. And if you threw it upwards, the reverse happens. Kinetic converts to potential on the way up.
That's a really clear illustration. The chapter also mentions applying this to a simple pendulum.
Qualitatively, yeah. Think of a pendulum swinging. At the very top of its swing on either side.
It stalks for an instant.
Right. Velocity is 0, so kinetic energy is 0. But it's at its highest point, so potential energy is maximum.
Then it swings down towards the bottom.
As it swings down, it loses height. Potential energy decreases, but gains speed. Kinetic energy increases. Right at the bottom, the mean position.
It's moving fastest.
Fastest speed, so maximum kinetic energy. And it's at its lowest point, so minimum potential energy. We often call this level 0 potential energy.
And then it swings up the other side.
Kinetic energy converts back into potential energy as it rises and slows down until it reaches the peak on the other side, 0 kinetic, maximum potential again.
So again, it's this constant swapping back and forth between potential and kinetic energy.
Exactly. And if there were no friction at the pivot and no air resistance, the pendulum would swing forever, with its total mechanical energy, K plus U, remaining perfectly constant.
But in reality?
In reality, of course, there is air resistance and maybe some friction. These forces do negative work on the pendulum, Bob.
Taking energy away. Where does it go? It can't be destroyed.
It doesn't vanish. That work done by friction and air resistance typically converts the pendulum's mechanical energy into thermal energy heat. The air molecules get jostled a bit more. The pivot might warm up slightly.
So the energy is still conserved. It just leaves the mechanical system of the pendulum and dissipates as low-grade heat into the surroundings.
Precisely. The total energy of the universe is still constant, but the useful mechanical energy of the pendulum gradually decreases. That's often called energy degradation or dissipation.
Okay, so wrapping this up then, we've really dug into work needing that force and displacement in the same direction, WSX cos theta.
Measured in joules.
Then power, how fast work gets done, PDOTZ or PESCV.
Measured in watts.
And energy, the fundamental capacity to do work, comes in many forms, potential, kinetic, chemical, thermal, etc. Also measured in joules, but also kBDUH, calories, EV.
And the huge overarching principle, conservation of energy. It just changes form.
It really ties everything together, doesn't it? How work is energy transfer, power is the rate of that transfer, and energy itself is this conserved quantity that makes everything happen.
It really does. Understanding these three concepts, work, energy, and power, it gives you such a fundamental lens for looking at almost any physical process, from throwing a ball to running a star.
Absolutely. Okay, so here's a final thought for you, the listener, to chew on. Building on that friction idea, we see energy seemingly disappear all the time, right? A car braking to a stop, a hot cup of coffee just cooling down on the table. We know the energy isn't destroyed.
It has to go somewhere.
So where does it really go? What forms does it take? Thinking about that trail of energy, where it ends up, even when it seems lost, that really opens up a deeper appreciation for conservation and maybe for things like efficiency and the way the universe tends towards, spreading energy out.
That's a great point. Where does the energy flow?
Yeah. So maybe take a moment today or tomorrow, just look around and try to spot examples of work energy conversions, and power in action in your own life. You might be surprised how much physics is happening right in front of you.